All right, the goal for today is to use the second derivative test to classify stationary points. This is an extension to what we did on Wednesday. Hannah and Stephanie, you were not in class, so you might be lost unless you did what you were supposed to and printed the notes from the online calendar and you went through the lesson on the website that was quoted. Okay. The substitute for today is the Honorable Mr. Rick Wheeler presiding. He was a former teacher of mine way back in the day at Bruce Junior High, and he will have no problem answering any question you might have of him today. So, Mr. Wheeler, I'm going to recite the question, and if you could press pause, let the kids have about 20 minutes, 15 minutes to work it through, and then press play again, and we'll see if they got it. Riley, pay attention. Okay. Determine the coordinates of all stationary points for the function 2x cubed minus 6x squared equals y. Find all those stationary points of inflection as well. That's a little different from yesterday. And sketch the function to scale and label all of these points. So press pause right now, and good luck to you kiddies. All right, welcome back. We want to find the stationary points. So we all know that the stationary points occur where we have a horizontal tangent line. So we find the derivative. The derivative would be 6x squared minus 12x. The derivative must equal 0 for a stationary point. So we must state that. Algebraically, factor. Factor out of 6x, and you get x minus 2. The roots are 0 and 2. Therefore, we can say we have a stationary point, number 1, at 0 something. Stationary point number 2 at 2 something. To obtain the y value, we refer back to the original equation. If you forgot, it's right here. Mental math. 0 in for x becomes 2 times 0 cubed minus 6 times 0 squared is 0. Stationary point 2. 2 cubed is 8. 8 times 2 is 16. 2 squared is 4. 6 times 4 is 24. So we have 16 minus 24 is negative 8. So we know a lot about the graph already. So why don't we sketch what we know, and then we'll worry about the inflection points. We're going to break out a graphing calculator to draw a good part of this curve. Wait patiently, Cody. Cody, pay attention. It's okay, Cody. All right, here we go. Y equals. Just going to reset my defaults. Second function, memory, reset defaults, number 7, reset defaults, enter. Yes. All right, we're ready. So, 2x cubed minus 6x squared. 2x cubed minus 6x squared. Whoops. 2x. What is wrong with this calculator? 2x cubed. I go back. There we go. Minus 6x squared. Okay, graph. Okay, so I'll take this screen and I'll draw it a little better to scale with our example. Okay. All right, let's label what we know so far. In red, we have a stationary point here. It appears to be a max, but we're going to use the second derivative test to confirm that. And we have a stationary point here at a min. So this one here definitely seems to look like a 2, negative 8. and the other stationary point here is at 0, 0. As the question said, we need to establish that these are indeed maxes and mins. So therefore, we'll have to use the second derivative test. So the second derivative, which is the derivative of the derivative, would be 12x minus 12. Now, the second derivative test, as we took last day, showed us that if the second derivative at a stationary point is less than 0, we have a max. The second derivative greater than 0, we have a min. So let's try that. Second derivative test. F double prime of our first stationary point, which was 0, which would be 0 input, 12 times 0 minus 12. Notice that that solution is negative. So the second derivative test tells us that therefore SP1 at 0, 0, because the second derivative was negative there, we must have a maximum. Because as stated above, over here, f double prime of x was less than 0. And if you look at our graph, our suspicion was true. And the second one, we'll do it in red. F double prime of 2 is 12 times 2 minus 12, which equals 24 minus 12, positive. Therefore, we have a minimum, because the second derivative at that stationary point, input x, was greater than 0. And we pointed out that that relationship works within the context of minimum. So far, that's what our solution looks like. Something that's new today is the finding algebraically of the points of inflection. Now, we have our graph on the screen right now. Look back to your notes. What is a point of inflection? Seriously, look at them. Open your book, Riley. Oh, Riley, that's what I forgot. You don't write these things down. Okay. Inflection point occurs where the concavity starts to change. The bending of the curve starts to change. And you'll see, in green now, I'm tracing our curve. We have max, 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 max. And somewhere around here, the concavity is starting to change. It starts to look like a minimum. So I'm going to make a big dot here, green dot. And we need to find that point. It looks like somewhere around an x value of 1 and a y value of negative 3 or 4, somewhere around there. But where does the inflection point occur? It occurs where the second derivative is 0. Algebraically, I'll get into that next day. But for today, let's just accept that if the second derivative equals 0, we have what's called an inflection point. Okay, so back to the previous page. Let's go and grab the second derivative, 12x minus 12. 12x minus 12. That has to equal 0 for an inflection point to occur at. Therefore, solve that equation. We get 12x equals 12, x equals 1. So we have what's called an IP. IP at 1 something. Once again, substitute back into the original equation to obtain the y value. So it's 2 times 1 cubed minus 6 times 1 squared, which would be 2 minus 6, negative 4. Negative 4. And a lot of you might have to have estimated that because you didn't know how to find it algebraically. But now you do. So let's go back to the curve and let's label that point as well. So I'll erase what's in green here. At 1, negative 4, 1, 2, 3, 4, right here, we have an inflection point, 1, negative 4. All right, Mr. Wheeler, you may press stop for this example.